Hi guys. So welcome to week 2 of the Seoul Machine Learning Seminar. I'm actually doing this recording as like a kind of post-recording because the computer froze up during the live session. There were several interruptions anyway. We had a couple of surprise visitors. But yeah, so let's get started. I'll do my best to reproduce what we talked about. So again, these slides are taken from the Coursera machine learning specialization. And so they're not my slides. It's a partnership between University of Washington and Coursera. I just use these to summarize and it's educational purposes only for the meetup group. Right, and these professors here are who developed this. All right, let me get started. Okay, so yeah, the example that they use, the main example is predicting house prices. It's pretty relevant to what we're doing in this course because we're kind of, our team here in Seoul, we're looking at the Zillow data, which is not predicting a house price, but it's predicting an error that the Zillow estimator makes when predicting house prices. So it's very relevant for us and useful. Yeah, so just say you want to list your house for sale, but you're not sure how much it's worth, and there are different approaches you could take to try to figure that out. For example, you might just look in your neighborhood and see how much the houses sell for nearby. But of course, even in a neighborhood, there are still going to be differences, right? Like the size of your house or the age of your house, what condition it's in. All right, so looking here is a plot of price versus square footage, and yeah, you can see it's not really linear. There are large houses that are lower value than these smaller houses, but generally there's kind of there is sort of a trend. All right, so for example, this house here, even though this would be the size, there are two very close homes in size with very different prices. So one idea brought up for deciding is possibly having a range. Like, let's just say this is 1,000 feet, 1,000 square feet. Maybe this is 900 and 1,100, and you're looking at all homes in this range, and then you take the average. So you would get some middle value. So yeah, it could be sort of accurate. But the idea with machine learning is we want to do better, right? All right, so linear regression. Linear regression model, if we look at this equation here, f of x, meaning the function of this square footage that gives you the output, which would be the price. And you probably recognize this from middle school or high school algebra or whenever it was you studied it, but it's very basic. This would be the intercept on the y-axis, and this would be the rate of change of the line, or the slope. Yeah, so a machine learning algorithm would try to figure out these weights such that the price outcome is such that the error is minimized along this axis for each of these points. So the error is measured on a line that would be parallel to the y-axis, because that's where the error is happening. The square footage is given, right? We know the input, we know the square footage. It's the output where we need to predict, and that's where the error will be made. All right, so we can move a little bit, but yeah, basically the way the machine learning algorithms tend to find this line is they will kind of just throw a line down and then calculate the residual sum of squares, and then they will use gradient descent or some other form to get an idea of how could they maybe wiggle the room or the line, or put down 3, and then pick the best one, and then maybe keep the best one, and then generate 2 more, or whatever. There's different ways of approaching it. But yeah, basically the idea is to minimize or change the weights such that the residual sum of squares, and that's measured at basically these blue lines would represent the error, and we would square that, and then we would sum it across all points, and you want that number to be as small as possible. And the way you can minimize the residual sum of squares is by changing these weights. Right. All right, so yeah, and then let's just say we went through that process, and now we can predict based on the size. Here's our line that is, you know, the residual sum of squares have been minimized for all of these points, and this is the amount that you get. So yeah, it's different. The other one, the average one, would have gotten you this, and without any kind of line, who knows what value you would have come up with. You've been maybe talking to your neighbors, maybe guessing. So the idea is that this one could be more precise. Okay, so adding higher order effects, what we mean here is, do you want to try to model your, okay, rather than just a straight line, maybe you can use a quadratic function. And so maybe you'll have a curve, maybe you'll have something that does this, kind of wiggles back and forth. Yeah, so like in the presentation, they were saying that this person, Carlos, the other professor, said, it's not linear. All right, so let's try this quadratic function. This one probably does better. And you can quantify that. You can check the residual sum of squares, and if it's smaller, then it does mean that this indeed models these data better, these data specifically. Yeah, so basically by using another feature. This could be a actual tangible feature, like, you know, number of bedrooms or something, or it could be some kind of engineered feature that's like kind of like an aggregation or of other features, or constructed out of other features. All right, but here's the thing. You can make the residual sum of squares 0. So meaning that you can force the machine learning algorithm to arrive at a model that perfectly predicts these data points. So I believe there are 13 here. So most likely this would be a 13th order polynomial, and a very like seriously contrived model, I guess, that is overfitting. So again, the overfitting is coming back. We want to avoid that, because once you map a real house onto this that's not from this original data set, I mean, look at it, it's going to be like down here somewhere. It doesn't make any sense. I mean, maybe the actual house really is this poorly valued for some other reason, like maybe the house was on fire or something, but it's not going to be because of this model accurately depicting the real world. All right, so yeah, why is your house worth so little? Yeah, because you overfit. All right, yeah, so, and it's not useful if you can't predict data that are not included in your training set, then it is not a useful machine learning model. All it has done is memorize the data that you gave it. And as soon as you show it something new, it's gonna fail big time. All right, so even though the residual sum of squares of this quadratic function is surely higher than 0, this is probably a much better, you know, a much better model that will make realistic predictions on data that are not part of this data set. right, so how can you control for that? You can make a test set and a train set. So basically, of our, in this picture here, we have 9. And we keep 6, and we call them our train data. And then we leave out 3, which will be our test data. And that's where we will check once we model something that does pretty well on these 6. Now we check, well, how about on our test set? Is it overfitting or not? All right, yeah, and so this is covering that, the train set, test set, training error. All right, so like we said earlier, we're minimizing to find the weights, but now we are only looking at these errors. These ones are not known until we just check the accuracy on a test set. Okay, and something that wasn't mentioned in this portion of Coursera, but I did bring up to the members, is a lot of times there will be another set called the validation set. And the difference between the train set, test set, and validation set is, yes, the model is training on the train data, and then the test set is used to check for overfitting, or yeah, it's used to check the accuracy, to then say, well, let's go back to the train data and let's change the weights so that that accuracy is better. So in a way, you have this indirectly information about your train data is bleeding over into your model, because it knows from the evaluate, whatever metric you use, if it's accuracy or precision, the model is adjusting to optimize that. So the test set is indirectly influencing the model. So the validation set, it can be another set that is like truly blind, your model is truly blind to that data set. And it can be like, it simulates testing the model on real world data or truly unseen data. And that would be the validation set. All right, so looking at training and test curves. All right, so you have high error at this end with low model complexity. And as the model gets more complex, and for the example, so what we had linear, quadratics more complex than that, and then the most complex was that crazily overfit one, which was 13th order, because there were 13 data points. So you have this trade-off going on. But on the test error, you tend to have this point, there's going to be this kind of optimum. And beyond that optimum is where you're overfitting, because now, even though your error on your train set is going down, your error on the test set will start increasing again. And usually in here somewhere is where you want to, get your model. All right, yeah, so kind of we touched on this, but yeah, for example, you might add, there are other features that are important than just square footage of the house. It could be year built, the number of bathrooms, number of bedrooms. All right, so what you do is you start, you kind of, when you add more features, you're gonna go into higher order models. So assuming that the data is relevant, or the features are relevant, the more features you add does, up to a point, it can improve the model. But even then, you're eventually going to reach kind of diminishing returns. So how many features do you use? I'm going to look at that later in the actual regression course, with this being just a kind of intro. All right, so this part I'll probably go through pretty quickly, as I did in the meetup. It was, these are just other examples of what you might use linear regression for. So given, these features like performances in your courses and the machine learning specialization, the quality of your capstone project, and how much effort you put in, essentially, And that would translate to an outcome of how much your salary would be or increase or whatever it is that your goal is with completing this machine learning algorithm. Maybe you're making a business and your app or whatever it is you're building can attract more investors because it has integrated machine learning. You can use it for stock predictions, another application, tweet popularity, how many, depending on features such as number of followers, number of their followers, and etc. How much reach would your tweet have? Smart houses that can adjust these variables to say, like, keep your house at a good temperature, but with a minimal electric bill. So kind of optimization problem for these sensors, or using those sensors. So yeah, this was the summary of what they covered. And then what we did after that is we moved to our notebook where we applied these regression principles, but we did so with the Zillow data. So let me go ahead and start that up. And since this does usually take a while, because my computer's kind of lagging, I just wanted to point out that last night we had two startup founders who used machine learning in their startups. One was eLancer Japan, elancer.jp, and another one was called, I'm not sure if I'm pronouncing it correctly, but Space, and they use machine learning to kind of predict the best way to construct a building depending on the neighborhood and what are the rent rates per unit depending on the size and the size of plot of land and etc. It was actually really impressive. They showed it to us after we did the presentation portion, and it was interesting to see some more big projects going on in machine learning. And that's one of the advantages of holding our seminar, or our meetup, our seminar in the Bitcoin Center in Korea, Bitcoin Center Korea. It's located in Itaewon, which is a kind of international section of Seoul. A lot of travelers pass through here, a lot of digital nomads. So when you're in here, either having an event or possibly if you're a member and doing some co-working, using the co-working space, you end up meeting a lot of very interesting people, digital nomads, entrepreneurs, and etc. And I guess they saw our event. All right, so if we go in here, let me just open up our notebook and quickly go over what we did, and then we'll wrap up this recording. All right, I think I can probably make it through here without actually running, because a lot of this, the thing about this notebook is it just captures a lot of the outputs. So I think I can make it through. All right, so like usual, importing GraphLab. And then we loaded this, this is basically an S-frame saved in its native format or data structure called features with error. And it's the one from last week where we cleaned it up and we constructed a couple of features. One was the absolute value log error, and the other one was, which I added after the video, it's like a count of, I think 22 features that were selected because there was a distinction between 0 and no information. Because, like, for example, if it says 0 garages, or in the garage feature, it doesn't annotate when there is 0. It just leaves it blank. So we don't know if it's a missing value or if there are 0 garages in the house. So because there's not that distinction, I didn't want to count that as a missing value. But basically, the new feature is like a count for each home of how many of these 22 kind of defined by us as important features, how many of them are missing. And then we want to check eventually whether there's like a correlation between missing values in those important features and like a high error rate, a big log error between because the hypothesis was that if Zillow has more data, more features filled in about the home, it could more accurately predict the home price. So it's a hypothesis. It hasn't been checked yet. But yeah, that's the reason why that new feature was constructed. All right, so just showing this feature. All right, so GraphLab Canvas opens in another tab normally, but if you set the target to the Jupyter Notebook, this is the file extension, then it will just print in here. So basically this is just showing a scatter plot where the x-axis is the lot size square feet, which that's the area of the property, the land that the home is on. And the y value is the absolute log error. And the reason why I'm showing this is when we were going through it before, we saw that the higher errors all tend to be clustered down here. The values in general do tend to be clustered down here, actually. But yeah, so they just look like there was some kind of correlation, even if it's weak. All right, so what we did was we made a train set and a test set by splitting with 80% is going into the train data, and the test data is 20%. And setting the seed at 0 so that anyone who checks out this notebook can get the same results as we did, can replicate our findings. Yeah, and then we just called it, basically we create the linear regression model and name it the lot model based on the lot size. Yeah, so using the feature lot size square feet with the target, this is the value you want to predict, is the absolute log error. I'm going to see if we can use this to how well we can predict this. All right, so it chugs and outputs this stuff. Yeah, basically, then we look at the mean for the actual absolute log error of the test data. So this is that 20%, but what is the actual mean value? It's 0.06, right? So that's a magnitude. It's always above 0. I mean, the mean is. All right, and then we evaluate use the lot model on the test data. And basically we see that the max error is 4.66. So this is actually a very large max error. So to give you like a frame of comparison, let's go back up to our visual. All right, look, on this plot anyway, I mean, it looks like the highest is 2.5, the median on this plot. I mean, it's possible that something was cut off. But yeah, basically there is one point that is like off the chart, basically, from our line. All right, and then you have this metric is the mean, it's the mean error, basically, for each point. So the mean square error, yeah, so which is 0.15. This value is basically how much different, how big the error is for each point, but the mean of the error between our model, the line that this model made, and the actual output, the actual absolute log error. All right, so on the scale of the log error values, this is pretty large. So I'm going to say it's not really that great of a predictor. And you're going to be able to see that in the visualization. Yeah, so this is just using matplot library or pyplot to map the actual test data. These are the actual like log errors. And on this plot, you can see there are values that are almost 5. And then this is the line. This is what our model would predict instead. So yeah, it's pretty much sticking down here and just totally losing. It's not mapping this well at all. These are outliers. I mean, most data are down here. But yeah, generally not doing a great job. All right, the coefficients. Okay, so the standard error and this value here, the intercept. So basically the intercept of the line is going to be 0.06 or closer to 0.07 where it crosses the y-axis. All right, so then here are 4. So including our lot size square feet, adding 3 more, room count, tax value, tax amount, because these are others that looked kind of similar in a similar way. When you visualize them, you kind of see this clustering of the high errors in, near the origin. What's going on here is that we have 0. I mean, it was annotated as 0 by the original data set, and then -1 indicates that it was not specified in the data set. So it was either an empty string or there was no value there, meaning it was like a null. We changed it to -1. One thing that was brought up in the meetup is we need to clarify here, if you have 0 rooms, it means, what does that mean? I mean, it means there's no building, right? So then the question becomes, does the Zillow data set include properties with no land on them? If it does, then this is okay. But if it does not include property with no land, then we need to go ahead and just group this 0 with the -1s as basically unknown, right? Because it's saying, if by definition the data only have properties with buildings, you can't have 0 rooms in a building. So this all must be unknown. So I'm probably going to post on a discussion board to find that out. Okay, so what we did is then we built a regression model using all 4 of those features. So we made that list, and then we just set features to that list. And then we call this one my features model. So again, using the trained data with the target, trying to predict the absolute log error. All right, it chugged when we put that in. And now we have the two features, or the 2 models, sorry, the comparison of them. Here's the lot model, here's the my features model, both on the test data. All right, max error, it is slightly smaller for the my features model, but it's not really not that impressive at all, right? And this one's also this is almost the same. You want this number to get smaller. But yeah, and then this is a visualization that it's the same one we already looked at, but we just have it nearby so that we can compare with the new one. And so I'm not sure if it's just because of color, but it does look like this one is tilted up a little bit more, but still generally not, not really capturing. This is not a good machine learning model, but it's just, a demonstration of linear regression for our course and using it on our data. Really, we're gonna have to do some other stuff, and I did put some suggestions in the bottom of this notebook. We're definitely gonna have to have some kind of pipeline, right? So maybe you can try making an S-frame for only houses sold on a certain month, and then run regression on them. Maybe we could just add the month sold to as a like variable. There's also a whole, there are more features that we could have added. Try using more features in general. One of them could be the month and year that the house was sold. There are 50 something features. We only use 4. Is just to give like a very basic demonstration of regression. Maybe you can run regression with log error, okay, instead of absolute log error, which will have negative values. I think this is that might be a little troublesome. I'm not sure, because they're pretty evenly distributed around the origin on the normal log error. This is the magnitude, but it could work, or it could be useful to just try it, see what happens. And yeah, another idea is classifying first as overpriced or underpriced. So, which is basically equivalent to overpriced would be a positive log error, because the Z estimate would be bigger and it's the numerator. Underpriced would be negative log error. So maybe like predicting on that first, and then applying a different regression model to, you know, to the home, based on which like classification it was predicted as. So it could be like a 2-step. Step 1, classify it as overpriced or underpriced, and then based on that, which partition it's in, then run this, you know, linear or regression model. Maybe, yeah, just trying to get linear regression in there somehow. And then, yeah, there could be other ideas. We have a Slack chat, and you guys can come in there and talk about it. But yes, this is pretty much all we did. Very basic intro to linear regression. And yeah, thanks for joining. And I hope to see everybody next week, and maybe even some new people. All right. Thank you.